and there might be some others here. See, I think I saw Filippo in the list of names. These days I work at Belroy. I did a stint at the Queensland Functional Programming Lab and then moved on to writing Haskell and functionally flavored Ruby at Belroy. So that's been good. I will switch back over to the screen share now. Is that clear?
Looks good.
Okay. Yeah. All right, so basically what I'm going to do is assemble a bunch of different bits and pieces from libraries that already exist on Hackage, so we can sort of follow the derivation. And we're going to start with a sort of dodgy dependent sum type that shows up all over the place in the Obsidian verse. And you can do some pretty neat stuff with it. So the type looks like this. Dsum tag f where so the intuition here is that we're going to have a tag type that tells us what the A is going to be, and then this f is just some functor because it turns out to be useful to have that in a type variable. So if I cook up a couple of types that I might want to stuff in here, so let's say we could store a person, so we'll just have a record. And we'll store dogs in there as well. And most dogs are good dogs, but just in case they're not good dogs, we will carry a boolean around, just to be clear. And then we tag this. We use a tag, a separate tag type to say the sorts of things we want. So I define that. Like person tag says we have tag person. The dog tag is the tag for dog. If I bring up happy days. So what can we do with this? So we can construct, and I don't have the show instances yet, so we'll just pull the types, but I can say a dog tag, dsum constructor, identity, very good dog. That's a dsum tag identity, and I can make one for people as well. So if the tag says it's a person tag, and poor old Bob's in the retirement home. So is that making sense to most people? I'll assume so.
Oh, can you not see us nodding and giving you thumbs up?
I guess not. No.
Okay, we will speak up and
just the way I've laid out my windows. Sorry.
Understood.
Okay. Good. So there's a pattern you see now and then in JSON libraries where you'll get something like you get an object and there'll be a discriminator, so like variant person, and then the rest of the object will be fields for that person. And if you have that, then you have a person. If this tag is different and says dog, then you expect the rest of the fields to be the fields for the dog. And dependent sums are one way you can represent these that's quite handy if you've got if you've got the same type appearing in a bunch of places and a sum type doesn't feel quite right. So we can go ahead and give these dependent sums a from and to JSON instance. And so this is the sort of thing it will look like. So you parse out the variant, and then once you know what the variant is, you attempt to parse a person or you attempt to parse a dog, and then you return the assembled dependent sum. And in the to.json case, you render out a pair for the tag, and then you render the remaining fields of the thing that's on the right-hand side of the sum. And this is fine, but it's also quite tedious to write because you essentially have to rewrite this for every tag and sometimes also for different functors as well, depending on how you want to set up your instances. And so the goal of the constraints-extras library, as I can understand it, is to allow us to write things that are generalized over the tag and over the F. So we want to be able to get to a point where we can say, write these from and to JSON instances for dsum for some arbitrary tag T and some arbitrary functor F. So that's going to take us through building some bits and pieces from the constraints library and some other places around other things kind of look for traps. So let's give ourselves some instances on these because we'll need them. Deriving show generic to JSON from JSON. So the first thing we have to do is be able to write functions that can work across any key. And so these days we can do this with quantified constraints. So if I want to show the key dependent sum, then I want to go from a dsum tag F to a string. And this one like that because we don't have a show instance, and so we can say for any A, we need to have show of tag A, and that will work there. And if I switch back to the terminal, then I can say show dsum key with that, and it will fail because I haven't derived show for the tag itself. So doing the tag side is fairly straightforward. The constraints extra library actually has machinery to do this that predates quantified constraints. So you can actually fudge it on old GHCs. I don't want to go into the guts of it because it involves setting up a crazy separate module that I don't understand. It involves grokking ed commit code, and it seems to be less essential now that we have quantified constraints. But if you're in older GHC, you can still do it. But dealing with the value side, so the right-hand side of this arrow, is still a little bit harder. So what do we need to know to actually work out what constraints we need for some tag and some A? So if I want to show the right-hand side of a dsum tag identity for this particular tag, then I'm going to need show for everything that can appear in the right-hand side of a tag, like every type variable that can actually appear in this A position. So that's like if I want to show then I'll need show for person and show for dog. And once I actually have a value in my hand, then I can unpack it, work out which one I've actually got, and go from there. So the first thing we're going to need is a way to capture and pass around type class dictionaries explicitly. And so the tool for that is the dict type from the constraints library. So the dictionary for some constraint C is so if I have the constraint for C, then I can construct a dictionary for C. So if I say what's the type of dict, the dictionary for int, then it will happily let that through. If I ask for the dictionary for functions from bool to bool, and also there's no instance for odd bool, and that will fail to type check. And then when I pattern match on a value of this type, it brings the constraint into scope. And the second sort of fundamental piece is we'll need a type class to talk about the set of constraints that we actually need for any particular type. So So what's this? What is this saying? It's saying that to create an argdict instance for some constraint constructor C for some tag type, we need to provide the set of all possible constraints we might need. And then if we have all of those potential constraints, then given a tag that tells us exactly which A we have, we can get a dictionary back for that. So this will, I think, become a bit more clear when I put out the instance for the tag type we're actually using. So the instance for some constraint constructor C for tag, we need to provide the constraints for tag C is going to be C person and C dog, because these are the two types that can actually appear in the A of a tag A. And then to find the actual dictionary, the argdict for a tag is either a person tag or it's a dog tag. And so now we know in this branch we have to construct a dict for C person, and we know from the constraint on the method that we have both C person and C dog in scope. So dict will type check here, and dict will also type check here. And that's a lambda case. Are people following that, or should we pick at it a bit?
It's making sense.
Okay. I should point out also that writing this stuff out by hand is really dull. So ConstraintsExtras provides template Haskell that will generate it for you, but it's worth seeing what it's doing at least once.
Hey, Jack.
Yes.
What are the types of the two dicts there?
So this is going to be a dict person, and this is going to be a dict of C person, and this is going to be a dict of C dog. And we know that because we've brought that last type variable into scope by pattern matching on the different tag constructors.
Sweet, thanks.
So this gives us the stuff we need, but it's not especially ergonomic. So we can do a little bit better. We can say, let's give us an alias that says, you know, we want our argdict instance and we want all the constraints all at once. We'll say as so. So we'll set up a constraint synonym and we'll set up a function to actually use this thing. So has C tag AR. So if we have all the constraints we need, and we have a tag A, then given a continuation with the specific constraint in scope, we can get an R. So let's actually step through the type errors here. So I can name the tag, and then I can name R, and now I need to construct an R. And the only way I can construct R is a value of type R is with this R argument. But if I just put that there, it'll complain because I don't have CA in scope. So I need to know what A is, and I need to show that I have CA in scope. So if I pattern match on argdict tag, then I know this is going to give me a dictionary. And it's going to complain because it doesn't have any idea what the thing actually is, because it's too ambiguous. So we'll ask for that, and it will complain because it's not enough frames. And so you'll see what's different here in this type error. Type error this time is we now have constraints include CA, and that lets us put R here, and we now have a thing that works. So if I reload this, the has function is specifically set up to use type applications. So if I say has for the show constraint constructor, then you can see it's going to ask the continuation will have show A in scope. If I pass in a person tag, and we'll say, okay, well, if person, show person is in scope on the right hand side. And so we can use this tool to write a more generalized thing to show the right hand side of a dependent sum. So show identity. So if we have a way of getting show given a tag, we have a dsum of some tag t or some tag tag, and we'll stick with the identity functor for now. Then we can get a string. So what do we have here? We have a dsum value, so we can pattern match on that. And then on the right hand side, we need to construct a string. Switches back to check errors. So we can say, because we know that we have, if we say has show tag, then that will bring the relevant show instance into scope. So you can see now we say constraints include show A, even though we don't know anything about this A except that it's the A from the tag. So that gives us what we want, and we can say show A, and that works. If I don't have this has show here, then it complains and it doesn't, it just needs to be led by the hand to know that we can actually find this show dictionary. So we have to put that in. And then once we've got that, we can say that we can show the right-hand side of any identity, any dsum that's using the identity functor without knowing much about the tag at all. Right? We need the tag to have an argdict, but that's easy. We can get that from template Haskell, or we can write it manually if we want. And so we're part of the way there. We've managed to generalize spitting out shows or type class using stuff in general, from our specific tag to a general type parameter tag, but we still want to be able to get rid of this this identity and talk about any functor. So are people following along so far?
Yep. Yeah, looks good.
There's lots of nodding, Jack.
Excellent. Unfortunately, Zoom only really shows me one face at a time, and I haven't quite worked out how to change the layout. So, yeah, I appreciate you telling me. So what we're going to do is we're going to, first off, do a cool trick to let us write sort of a function composition of constraints. So if we have f of GA, we can say we have compose C and instance So this is kind of like the functor composition new type, except it's working over constraint constructors instead of constructors. And so we'll use this to say a compose C of some functor f with the constraint we actually want, and use that to replicate our has machinery to work with an extra type parameter for some functor. So first off, we'll make a bit more room in constraints 4. So before we had constraints for a tag and then a constructor. And then we'll also say that there's an F in there. I must get a prime one because it's the same but different. And then in our constraint alias, we'll say we want the argdict for compose C CF tag. And sorry, I'm reading ahead in my notes. This is the constraints for the same tag, but with C and F composed. So if I say what's the kind of constraints for prime, our tag type, show identity, it's going to ask for compose C show identity person and compose C show identity tag. And then when GHC goes to expand those instances, it'll ask for the show, an instance for show identity person. And that gets us what we want. And then we can use that to write a lifted version of has. So it has prime for some constraint constructor, some tag, and then some F. We need the argdict for the composition and that tag, and then that constraints for prime tag CF. And once we have has prime, we can write argdict prime. So for some constraint constructor C, some functor F, our tag type, some A, and some result. Then if we have everything we need to has prime, And given the tag, and given a continuation where we have that constructor in scope over the so the constraint is now over the FA instead of just the A. So this will let us look at the right-hand side of a dsum properly. So argdict prime, the tag, we just delegate to the one we had before. And we may need to help it along. So we say it's columns again. Tag is dict.
So Jack, is this the equivalent of has? This is like.
So this is the equivalent of has. I've merged. So instead of tag A, we don't want all of this. We want the dictionary for CFA. Makes sense. There we go. Then once you have that, you can construct a lifted has. And once you have that, then you say, oh, and what's that complaining about? Has prime C tagger. Oh, you name the tag as well. There we go. So this gives us has generalized to accept a functor parameter as well. And then this gets us all the way to be able to start writing proper generic instances for dependent sums. So we had the key side before. We need to be able to say for all A, show any tag. And if we have show for the tag and the functor on the right-hand side, then we can say we have show for the sum itself. And then I'm going to write dodgy show instances. That's okay. We need to construct a string. So we can say show tag, which is fine, because we know that tag has a show instance for any A, which quantify constraint gives us that. And then on the right-hand side, we need to bring in the specific show instance for FA in the scope. So it's the same trick as before. So has prime will let us do that. We'll have no idea what the types involved are. So we want has prime at show, and we want it on F. Once we have that, and we pass in the tag so it knows what A we're talking about, we now have show of FA in scope. Once we have that, we can use it. And now this lets me go all the way back to here, and I can just show things. And if I actually emit something that looks like the constructor, you might even be able to read them back. So to wrap this up, we want to actually circle back to what we started with and be able to parse up some JSON. So we're going to need to parse the tag into, well, we don't know what the A is going to be until we parse it. So we need a type to contain that. So the sum F, use the GADT, where sum stores sum FA, but we don't know what A is. And we'll get the instance for that. So that gives us a way to a type into which we can parse the key, and so we can write the Fromjson instance out. Instance Fromjson for some tag, we don't know which. So we expect to parse some text. The person is going to succeed. Person tag. Dog is also going to succeed. And everything else is going to fail. We can go the other way as well. Instance 2 JSON. We don't need some because at this point we know what the tag VA is. So that's fine. So this gives us enough to read out some tag out of that variant slot that you often see in JSON APIs, because there's not really a good way to encode algebraic data types into JSON that I've seen. So once we have that, we can construct from JSON. So to construct the from JSON for dsum tag F, and you probably wouldn't do this without a new type in reality, but anyway. So to do this, we will need to be able to parse the tags, and we will need to use hasPrime. So if we can parse some tag, and we can get a from JSON instance for every FA that tag might want us to construct, then we can parse interdependent sums. So parse JSON is going to look a lot like your fairly normal ESIM code. When we parse a tag, we get to bring a type variable A into scope. Once we have that A, we can use has. We know the constraint we want to get out of it. We know the F. Now that we have the tag, we know what the A is. And here, we are going to be asked to complete the parse, and we have the from JSON for the FA in scope. So we can say we can parse it and construct it. And now it's complaining because the instance that I threw together at the start of this talk is getting overlapped. So we will delete that. If I reload and I say to decode from I'll to decode a We've successfully parsed our dependent sum out. And you can also parse the dog out with different JSON, and away you go. So what else do I want to say about this? So this little wrapper has been split off into its own library called sum, S-O-M-E. All of this machinery lives in ConstraintsExtras and is quite heavily documented. The documentation hasn't landed on Hackage yet, but it is in the source files at least. And the dict type itself is in the constraints library. Dependent sums and dependent maps are actually quite pleasant to work with when you're dealing with sort of the kind of awkward data types that you get when you work with JSON APIs, because you can, the dependent map type in particular generalizes this thing to kind of sets of these things. So you have a bunch of keys, you know what the values will be at each key if they exist. And so this lets you get a bit of extra type safety. And then once you have this sort of machinery, you can do your type classy sort of stuff across your dependent sums and maps much more easily than you would otherwise. And you don't have to restrict yourself to kind of ad hoc instances for just the tags and classes, the tags and functors that you're working with. So that's it. That's a rough overview of how it all works. And I suppose we go to questions now.
Thanks, Jack. That was really good. Can I ask a question? What template Haskell things do you have to prevent writing out some of the instances from that?
So it's not me, but you can the Obsidian Rotor maintain this library, but this tag type instance goes away, and you basically write, I think it's derive arg dict tag, and that's the only thing that needs to be written. Once you have that, then it can go off and use has and has prime and everything else. So that makes it a fair bit more pleasant to play with.
Cool. Any code that I don't have to write is good code.
Agreed.
Can you show an example of what it looks like when it fails to decode? Does it just give you nothing, or do you get like where you had a failure there? Can you get a little bit more information out of that?
Is it decode either, or is it either decode? I always forget.
Who goes for?
All right, so if I change this to either decode variant Steve, then it's showing the part of the structure that failed. I put the wrong tag in here. I try and parse this record as if it was a dog. Then it's committed to parsing it as a dog because it parsed the variant successfully, and then it's found missing. It's failed to find the keys it needs to complete the parse.
It would be nice if it could dump out what it's already committed to parsing, because it's kind of telling you what's implied by parsing dog rather than telling you, well, yeah.
Yeah. So
if you know what I mean.
Yeah. So I imagine you could put something a bit more explicit here, possibly using the alternative instance.
I'd be surprised if you couldn't extend the error stuff in Eason to say something at the beginning like for variant whatever, couldn't parse blah.
Yeah,
Yeah.
it's already extended. You see how it says error in $.variant? So you can do a similar thing. I forgot what it's called, but you can put an additional string there.
I used to know how this worked because we stole all of it for something we used at Seek.
I personally prefer the kind of value level parsers and encoders with applicative and contravariant instances, but this is a nice motivating example for doing all the constraints extra stuff. So I went with Ethan because everyone knows Ethan.
So Jack, it seems to me like the power of this comes from when you need to start extending this. So if you added a cat to this, how much work is it to now add cat?
All right, so I need a data type for cat. And so we have a cat tag. And then this is complain. Then you'd get this for free anyway because we come from template Haskell. And constraints for would also be extended, but that would also be template Haskell. Argdict prime, I put the wrong thing there, that's fine. So you need to parse these. And I think we're done. So if I want to parse a cat that's got only a few lives left, then yeah. So why do I like this? So that using the dsum stuff means you avoid kind of the awkwardness of the record, trying to have records inside a sum type to some extent. Like you're probably going to end up having separate record types anyway, and having a because you're gonna end up having separate record types hanging off each constructor, whatever you do. But then capturing the pattern for it means you can abstract over it, which is a bit nicer than writing a sum type for everything. And if you know, if you have a bunch of like an object that may have a list of people and a list of dogs and a list of cats, then you can use the tag types in a dependent map to make sure that you get the right things coming out at each key without having to worry or deal with something as kind of undisciplined as a hash map of text to JSON object or something like that. You can deal with kind of the gnarly sort of JSON you get in APIs a bit more nicely.
What is there anywhere else that you've seen people using this dsum technique? Any other examples?
Andrew McMillan used it a bit in a talk on at Compose a couple of years back, where he was using it with property-based testing to manipulate the WordPress API. I think it was WordPress. Because
Yeah.
So he had Hedgehog running, I think, starting up and spinning down a VM of WordPress, and then just hitting it with the property state machine testing hammer and finding bizarre bugs. It shows up a lot in the Obsidian universe sort of code. So I think that it's something like in the guts of Reflex, where you want to pass a map of every event that's fired in the current frame, and then that's like a heterogeneous collection of event tags and the values with which they fired. I forget how they generate the tag type to make that work. Ben, you might know.
I don't know exactly how that tag type is generated, no. But there's a bunch of them for like constraining. I can have these kinds of things at this spot, and I might have some, I might have whatever, but just having that sort of heterogeneous map is really cool.
Yeah, so the fire events method inside the guts of Reflex host takes a list of dsum where the tag type is event trigger of T, which is the Reflex timeline, and identity. And I forget exactly how that works, but you can dig in under that somehow.
This dsum is also parameterized by a functor f. Can you show him
Yes.
how it is used and why?
The vast majority of the time it's used for I find myself just using identity here. So if you have and again, Ben, you might be able to speak more to this, but I think in the Obsidian codebase they use it a lot to use the same structure to talk about the things I might be interested in. So if I have a map, so if I don't write the implementation, but you take it on faith that dmap tag f exists, and so this is like a collection of dsums in some sense, where you have each key appearing at most once, each tag appearing at most once. And then if I say something like a dmap of tag, I'll just comment this out so fly check doesn't crumble. So dmap of tag proxy is like the set of topics I might be interested in. A dmap of tag const something will give you a sorry.
Yeah, the reason why that is useful is because in a lot of Obsidian apps they use this big sort of dsum to represent the entire state of the app, and by using the proxy, it's a thing with no holes to put in, and const is
Like
a different
the
way.
actual values.
The actual values, yeah.
So const is like the query that you can put through, and so if you have a type family that says like compose const query args or something, then it can tell you what args you need to make a query for something at that tag position, and the map tag identity is the thing that comes back.
And it's useful being able to wire a sort of error correcting like an error handling functor as well for like validating forms and crap like that. Just having that functor there means you can reuse that structure over and over again for different behaviors, and it's really, really, really useful because you don't have to keep writing those data types over and over again.
This kind of stick a type parameter in and use it over your entire structure is just really handy in general. You can, I assume you'd be able to get all of the rank 2 classes sort of instances, right, as well. So like if I had I could go from a DMAP tag compose FG to a F DMAP tag G, right? So this is like sequence lifted. Yeah.
There's fanciness that you can do there.
I don't know exactly which library they tend to use over there, but there's I tend to go for rank 2 classes. I think Conkin gives it to you as well, but you can basically like derive the functor applicative foldable traversable stuff over a functor parameter instead of an A. So if I have so traversed is A to FB. I'll do that off the top of my head. Let's do FMAP. FMAP is A to B, FA, FA to FB, and then rank 2 FMAP is like for all A, for all A, FA to GA, then I can turn a KF into a KG. And so this is like, I can map values, and this is like, I can hit my structure with a natural transformation, or something that we call a natural transformation in Haskell, but it's actually a bit more stricter. And then you can do traverse 2 is going to be roll A, if I can turn an FA into a G of HA, then a KF can turn into a G of KH. So you can see it's kind of got like the same sort of flavor, but it's operating on functors instead of on individual values.
Hey, Jack, coming to your DMAP stuff there, I'm just trying to get my head around it. Is a DMAP tag F a structure that for every value of type tag, you can get back out something of type F, FA? Or is it a subset of all of the tags? I'm not sure if that was clear.
It's kind of like you could model it as a list of dsum.
So it doesn't necessarily contain one of each tag.
So no, it's like a data.map.
Yep.
That's been generalized. And with the additional constraint that tag does not appear twice, right? But you can model it with a list.
Is there a structure that gives you that sort of like guaranteed one-to-one lookup? So if you've got a thing of tag F and you give it a tag A, you get back an FA, like you're guaranteed to get back an FA? I'm not sure what that would look like.
That's a function, right?
Oh, maybe. Yeah, I guess.
Yeah, it's like a function that's been turned into a table.
Yeah.
And I've sometimes wanted this at like not at the DMAP level, but just like the normal values. But I haven't found a library I liked.
Because it looked like one of the places where errors could sneak into the code that you've got below was the string for each tag. And if you had a one-to-one mapping between tag and string, then you can automatically build that the two bits of code that look up by tag. And
so I think, yeah, quite right. So I could write string key for is going to be tag tag A to string, right?
I guess the other one would be the string to maybe some tag. Is that right?
DMAP. Yeah.
Oh, so
yeah.
The other direction. Given a string, give me back some tag. Anyway, we're probably getting a bit off topic. Sorry.
Yeah. So I could. So yeah, I kind of need a type class that lets me say something like I can get the universe of all tags, like a type class that means that it's like finitely enumerable.
Yeah, it's called data.universe.
Or lazily, or at least lazily enumerable. Yeah, and so you probably want something like a universe of some tag. And then once you've got that, you can feed that into the string key for function to make sure you parse each possible thing properly. And you can like map this across the universe of some tags, and then sum it together with alternative, and to JSON here is like packing string key for, right?
That example that I put into chat of crazy dsum and dmap stuff has an example of using universe through all the constraints-extras stuff. So if you want something that's like shows you the maximum power of what you can do with all this kind of stuff, that's a pretty good example if you want to dig into it later.
Finding the storage of the app as a DMAP, and then yeah, that sounds like it will be good doing. Dave Lang gave a talk at Lambda Jam a couple of years back titled DMAPs for Delightful Dynamism. You probably want to watch it on 0.75x speed because it just goes at 100 miles an hour and doesn't stop. But it will tell you where most of the major milestones are in the landscape, I guess, rather than be a thorough tutorial on it. So it's it was an interesting talk, but yeah, it moves very, very quickly. And I think you just have to play with it.
At Obsidian, it's affectionately known as the DMAP speedrun.
Yeah. Yeah. DMAP any percent speedrun, glitchless.
Awesome. Well, if there's no more questions, then we might thank Jack. That was a really interesting talk. Thank you.
Thanks, Jack.
Thank you.
Thanks, Jack. Great talk.